Friends, we're going to be using these gas bottles to make a rocket stove barbecue. This is where the idea for this Rocket Stove Griddle barbecue came from. It was making rocket stove just from bean cans at a camp out. That was really great, but I wanted something a bit more epic in scale. I already had the experience of making a rocket stove heater for the workshop, which I talk all about in this video and assess it 5 years into its life. If you're interested in the principles and design of rocket stoves, do check that out in the link below. That's the background, but in this video we're going to be making a rocket stove barbecue griddle from this gas bottle. A great way to mark up any cylindrical object for cutting is to use a flexible flat square sheet. Line up the edges when you wrap it around and you're all set. I can slide it to where I want it, which is about there. Try a bit of the old black on black. So I haven't seen any of the rocket stoves online, whether cooking or heating. They use quite such a large diameter tube for the main body of the object. So this will be a bit of an experiment, and I'm not sure if it's going to work, but I'm quite hopeful. Okay, time for some cutting. So if you know a better way of cutting these old gas bottles, I'm all ears. Please do leave a comment below. I'm using 1mm thick slitting discs on the angle grinder. Obviously it's important to make sure the gas bottle is empty of any gas before you start, especially if that gas was flammable. In this case it was just CO2, so it's a little bit less crucial. As long as there's no pressure there, I'm okay. So the material making up the gas cylinders I've cut up in the past, the propane ones I used to make the workshop stove, were all 3mm thick. This is actually 6mm thick steel. It's really quite impressive stuff. As far as I can tell from the spark pattern, and it's normally just a guesstimate, it is mild steel. You can see here how quickly the discs get used up. So I've read that the ideal size for the feed chamber is approximately 2.5 times shorter than the main riser on rocket stove, so that's the kind of dimensions I'm going for. So it turns out this is quite a complicated cut to get this pipe to line up exactly with this one. We need to cut what's called a fish mouth or a saddle cut. So to do that, I've printed off from one of these online templates just a wraparound thing. I was really surprised at how well these online template things work. You just enter the diameter of the pipe, the angle it's meeting the other pipe, and so on, and it prints you out a nice template thing. It makes it so simple. I'm just marking around, using a Stanley knife to cut away, and then the mighty angle grinder to get it stuck in there. So with all this cutting, I thought I'd experiment with this alligator saw thing and a metal cutting blade, and it was woefully disappointing and didn't really get anywhere. With the gas bottles in the past, I've had quite good luck using my jigsaw, which seems kind of similar to the alligator saw, but that was no good. Now friends, when you watch these videos, I hope you appreciate how long it takes me to wiggle jiggle things around and the thinking time involved and just how much gets cut out of these videos. In this case, this was really impressive. It was just straight out of the gate. The saddle worked perfectly. So much so, I actually just felt like I had to sit and think for a while anyway. Let me know in the comments, do you want to hear more musing or do you want more action? Okay, this is good. So we're basically there with this. So what I'm going to do now is reach through there and mark the hole I need to make in this one. Okay. There's definitely a technique to doing these plunge holes with an angle grinder and making the edges smooth, and I think I've gotten a little bit better. I'm not sure what the secret is really, other than practice. Tilting the blade slightly away from the cut will tend to round the edge or cut more of a curve, but there's only so much you can do that really in 6mm thick steel. That's especially true when you're using the thin 1mm slitting discs. I could have used another one of those cool online templates to make the hole in the riser that this is fitting to, but it seemed prudent just to use the shape that I had to draw around that, which is what I did. Of course, the edge of all this hole wants to be nice and smooth, so sticks and whatever you feed in there is not going to snag up. The gravity feeding element of these rocket stoves is one of the main benefits of them, so that's quite important. Quite rusty bit. Rusting away in my hand. The cool thing about the power hacksaw is that it means you can get on with something else while it's cutting. In this case, this is some freehand straight line cutting with the angle grinder. So this hole is quite multi-purpose. It provides a good amount of air for combustion. It's also where I start the fire from in the rocket stove, and it's also where you can clean the ashes out. My initial measuring stroke guessing wasn't quite what it should be, so I will definitely need to cut this rusty bad boy down a little bit so that we can reach in and the propane torch will fit in there to light it up. My feeling is that a good blast from a MAP gas or propane plumbing style torch is the way to light these rocket stoves, because it gets to clean burning temperatures much quicker, which means you're not polluting with partly combusted gases and it's much more efficient burn. It's not ideal, but a little bit of work on that. A good number of these discs. Got a small. Let's have an interlude to go through a small bit of theory with the design of the rocket stove. So ideally you want the airflow of all the combusting gases to come in to be about equal to the flow of exhaust gases, and that keeps a really efficient burn. So this is a 7-inch tube. That's a diameter symbol. And that's approximately 38.5 inches squared of area available for air to rush through. This one's the same. This is going to be the gases coming in to the combustion area here, and exhaust gases going out here. We want to unify this, so you might think, yeah, great, same amount of air coming in as going out equals good. But this area is the fuel magazine, so when that's loaded with lots of sticks, the available space for air to rush through is much reduced. Let's say that's approximately a quarter or something like that. So if we say that's 10 inches squared available there, we want to come as close to possible as 38.5 inches of available air for combustion to occur, which is where this comes in. That's coming here at a slightly offset angle to try and create a vortex in the burn chamber, which makes for more efficient burn. Anyway, this is a 4-inch squared tube, which means it's 16-inch square available area, a little bit less when you take into account the wall thickness, but let's just say 16 for now, which gives us 26. So we still want to find quite a bit of extra air coming in, which is where this thing comes in. It's going to preheat air, and then we'll have hopefully some air at the back as well. Right, enough with the chit chat, let's get welding. This is how the table converts to welding table. Normally I've got that wooden plywood sheet on for woodworking assembly and other MISC tasks. So I've spent a long time whizzing off all the paint with a flat disc on the angle grinder, like an inch round all these welds before tacking it up. For these welds I'm using the highest setting on my MIG welder along with a high wire feed, and that's to try and get really good penetration and weld strength. It's easy to get welds that are pretty on thick material using lower settings, but they can be very superficial, not melting the base material enough to get a proper joint. In fact, for 6mm thick steel you do actually need quite a powerful welder to really get a good joint. Following the tack welded assembly, I'm using a fairly standard seam welding method where I'm kind of going an inch or so at a time. That helps prevent excessive warpage, but also in this case it stops the paint from melting off and filling your life with fumes. I was actually a little bit wary of this internal weld I would have to do, but it actually turned out really nicely. I was a little bit surprised. And now looking down the tube, not really any light coming in. And then external inspection, it all looks great. It's been a little bit tricky to get this clamped on how I want it. So here we go, the idea is the air's going to come in along here around the outside, getting nicely preheated against this edge before coming in here at a nice tangent angle. Wow, that was epic and ridiculous. Don't do it that way. This snagging here is the only problem. It's just so close up the top here. You know what I'm doing with this barrel over the riser anyway, right? Well, this method of getting it on I really do like. It makes a really tight joint, and without having to weld the really thin material of the barrel onto the super thick material of the riser, which would be very difficult. The slight miscalculation down here where I'm having to adjust it was unfortunate, because it's very much a one-way process, this thing. It slides in one direction, but if you try and shift the barrel in the other direction, it totally grips on and is incredibly strong. So you can actually lift the whole thing now using the handles on the barrel. It's also a very tight fitting seal that you don't need to weld with, and it doesn't need to be super accurate when you're cutting it. I'm now using some more of this channel material to fabricate another preheated air inlet. This time it's going to be very much for secondary combustion, so it's going to be higher up the flue. The idea with this is that even if all the oxygen's been used in the primary burn down in the main burn chamber, there'll still be some supplied, so the flame will continue on up. It's taking shape, it's become quite heavy. So I calculated how many 8mm holes I'd need to drill in the steel to equal the amount of air coming through that channel. It ended up being way too many, so the holes ended up being like the beginning and end of some slots that I was desperately trying to cut at a really like steep tangential angle, again vortex forming. And then before putting that channel on, I think we can improve the preheating somewhat by getting some fins welded to the body there. That's just going to increase the contact the air has with the surface of the hot metal. I continued with the upcycling theme and used odd bits and bobs, so it looked pretty awful, but it's all behind the air channel anyway. So it is really nice on experimental things like this where you're not 100% sure and it's prototyping, to be able to control the airflow is really quite nice. Right now I'm just welding on some scrap steel just to stabilise the base a little bit. Oh, and there goes the trip switch, which does happen occasionally when I'm welding up maximum amps. Come on, it stands up. Let's give this baby a try. It's really started going now. Back here, we can see the paints bubbling off. That's it. That is the power unit. Friend, if you made it this far, I salute you. There were some geeky details in there, and like me, you are obviously Rocket Stove interested. So let's do connect in the comments below. To turn this into the Rocket Stove Griddle / barbecue that it just wants to be, you're going to have to join me for the part 2 video, where I take some random household items and upcycle them into a preposterously efficient barbecue griddle. Apart from that, check out my adventures in stovetop fan upcycling, or my 5-year review of the experimental rocket stove style workshop heater.